Let's work an example using the Orsat analysis to understand what our fuel is. So in this case, I have a fuel. I know it's a mixture of methane and ethanol. Okay, so methane is CH4 and ethanol is C2H5OH. We're going to burn this with air, and we have the Orsat analysis. Based on this, we want to find the balanced chemical reaction and the air-to-fuel ratio. So this is what the Orsat analysis came in as. 12% CO2, 3% CO, and the balance is nitrogen. And based on this, we want to determine how much methane and how much ethanol we have. So let's start by writing our chemical reaction and begin doing the balancing process. Now, I do this by, I know I have some CH4 and some C2HO5. I know I'm going to have some air, and it's going to make CO2, in this case, some CO, nitrogen, and water. So my normal combustion products, plus I know for a fact that it has some CO. Now, I'm going to use the Orsat analysis percentages as my coefficients. It really doesn't matter because in the long run I'm looking for percentages or an air-to-fuel ratio. And so if I'm looking for ratios, the specific values I use does not matter. So it's easiest, less likely to make mistakes, if I use percentages as coefficients. So 12 moles of CO2, 3 moles of CO, and 85 moles of nitrogen. And I need to figure out what all these other coefficients will be equal to. So this time what I want to do is I want to start by balancing the nitrogen because I know that the nitrogen that comes out came in, right? So very simply, if I know I've got 85 moles of nitrogen coming out, then I had 85 coming in, I need to know how much was in it as air, so dividing by 30.76 says I have 22.6 moles of air, or 22.6 moles of oxygen also. So now then I know how much oxygen I have because I did the nitrogen balance. Alright, so what am I going to do next? Well, the next step is going to be slightly more complicated because I don't really have like a clear-cut approach. So what I find it easiest to do is put in coefficients. So I said that I had A moles of C2H5OH, B moles of CH4, and C moles of H2O. Those are the things I still need to solve for. And then I set up balances on the various kinds of atoms. Now, I've already done nitrogen, so I don't need to do that one, but I still have C, O, and H atoms to consider. Carbon occurs here, 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 and here. So I have, for every mole of A, I have 2 carbon atoms, so 2A, and I have one carbon atom in the methane, so B carbon atoms. On this side I have 12 and 3, which is 15, not 25. So I have this as one reaction, or as one equation. I also can balance my oxygen. I have 1 times A, 0 times B. Here oxygen appears twice, so 2 times the 22.6. On this side I have 2 times 12 and 3 times 1 and C. And finally, if I were to do the same process on H, I have 6 H's in the methanol or ethanol. So 6 times A, I have 4 in the methane, so 4 times B. I do not have H in the air. CO2 and CO also do not have H. No H here, but I have 2 C in the water. So this gives me a system of 3 equations and 3 unknowns. Now we need to solve that, and you can solve this by any method you'd like, whether you'd like to do substitution or whatever is going to suit you. Personally, I find that Excel is very handy for this, and so I'd like to take a brief moment to show you using Excel to solve something like this. So if I have this as my balance, I've got an equation. I did a balance on C, carbon, oxygen, and hydrogen atoms. If you set these up as coefficients 2 and 1, so 2a and 1b equals 15. Again, let's go back and look at this. 2a plus 1b equals 15. And continue doing that for each of these, for O and for H, the coefficients of A, B, and C and what they are equal to. Set this up as a matrix equation, so it's of the form AX equals B. What I want to do is solve for X. X is the coefficients, the values of A, B, and C. So if I were to do that, I could solve this using matrix techniques as A inverse times B. Now, I assume that some of you have probably not done matrix math in Excel, but it's really not hard. The real trick is that you're going to, when you start, you're going to highlight the correct size of your answer. So you start with that, then you're going to type in the appropriate formula. And once you've done that, then you're going to end with Control plus Shift plus Enter all at the same time. All right, so let's demonstrate that. So if I wanted to take the inverse to find A inverse, and this is my A, so these are my A's right here. Okay, then to find the inverse, it's going to be the same size, so I highlight 3 by 3 group of cells. I type in equals M inverse, that's the formula, and I highlight the array as it says. Now then, before I hit enter, I want to push Control Shift and then enter all at once, and it does the calculation. So this is the inverse of this matrix highlighted in red. Now the answer is going to be the product of the inverse times the equal to side, right, the B. So A inverse times B. So again, I'm going to highlight the size of the answer. I want it to be a column just like this was a column. So I'll highlight that size. I say equals, to multiply matrices, the function is mmult. I want the inverse times, and I put a comma to separate the two arrays, the B's. So I've highlighted them, I've separated them by a comma, I close my parenthesis, and then again Control Shift Enter. And I end up with the answer. So I have 5.9A, B is 3.2, and C is 24.1. So I could have also done this, of course, using standard algebra techniques, but this is just simply faster. So if I look at this then, plugging those numbers in, rounded to just the tenths place, and I end up with this as my balanced chemical reaction. So what is the air-to-fuel ratio? Well, all I need to do is remember that the air-to-fuel ratio is traditionally done in mass. So I need the molecular mass of each of these. Ethanol, you can look this up online in a chemistry textbook, etc. 46 kilograms per kilomole is the molecular mass of ethanol. Multiply by the number of kilomoles I required, and it's 271.8 kilograms of ethanol. Now remember, this was based on just, I made up numbers, right? I said it was so many moles was what was produced. It's going to all be fine. Now I do the same thing for methane, excuse me. 3.2 kilomoles of methane were required, but the molecular mass of methane is 16.04. Multiplying gives me 51.3. The total amount of fuel then is the sum of these two. Now to figure out my air, there are several ways to do this, but a simple way is to take 22.6 times my O2. So this tells me how many kilomoles of O2 would be required on the same basis for these moles of fuel. But I need to know about air, not oxygen, but air. So there are 4.76 kilomoles of air per kilomole of oxygen. And the molecular mass of air is 28.97 kilograms per kilomole. And therefore, I find that there are 3,116 kilograms of air. Adding up my two fuels, I get the mass of fuel divided by the mass of air. I have a fuel-to-air ratio of 0.1 kilograms of fuel per kilogram of air.